Okay, here we have section 4.0, and we're looking at a definition and a theorem. Well, actually, a couple theorems. So this is introducing this idea of cofactors. And so the definition is simply that the cofactor denoted the cofactor based on ij of a is simply, okay, so I use a Cij of A, and all I'm going to do there is absorb the -1 to the I plus j into the minor of ij. Okay, so remember in the definition of the determinant, we always have this thing, that -1 to the I plus j, and then we also have the minor ij for that determinant of the submatrix. This just combines the two into one thing. That's all a cofactor is. But then with that, they make a new theorem. It's not much of a theorem, right? They just say, oh, well, we could write the determinant of A in terms of its cofactors instead of minors. So j equals 1 to n of aij times the cofactor ij of A, right? And that's for any I, any row expansion. And so it just kind of simplified the notation a bit, but that's also equal to the sum I equals 1 to n of aij and the cofactor ij of A for any j. Okay, so I can expand about any row or column. And again, it's just our original definition of determinant along any row or column, and we've just absorbed that -1 to a ij power into the minor aspect and called it a cofactor. Now, here's the bigger deal. So theorem 4.0.8, and that says if we go ahead and were to think about that, almost that definition of determinant, so we're going to sum from j equal 1 to n, so we're summing across the columns. We take aij, okay, so we've picked row I, but if we use a cofactor that is not the right one, in other words, so kj of A, so we keep row I, okay, we keep row I, but we throw out a different row. And so this says this will be equal, and this says if I is not equal to k. And then similarly, you can do it with columns, expanding about a column. So I equal 1 to n of aij and a cofactor, but this time throw out that column you're expanding by. Well, actually keep it in, I guess, not throw it out. A equals 0, and this is if j not equal to k. Okay. And so the way they prove this is, okay, we'll start with A, and then let B be obtained, okay, by replacing row K by row I in A. Okay, so they point out B has two identical rows. So we know its determinant is 0, right? So determinant of B is 0. And so then they say, okay, let's expand the determinant along row K. Okay, so that is 0 equals determinant of B. This is a pretty snazzy little proof. And then, okay, so this is just J equals 1 to N of BKJ and CKJ of B. Now, but that row K, what we'll do is J equals 1 to N. So remember that row K in B was identical to row I in A. And so I can do AIJ for that value of K. And, but now I'll keep this the same, CKJ. But since we were expanding on row K, every other row of B is exactly the same as every row of A. And so these two cofactors are the same thing. Okay, so we'll kind of look at this, and but that's how we get our 0 for this. Okay, so let's take a look at something pretty straightforward. So we'll take 1, 2, 3, and how about 1, 2, 4, and 0, 1, 5, something like that. I think that's non-singular. We can always check, but what this says is if I take this matrix and I expand, say, J equals 1 to 3, and I take, let's expand about the first row, A1J, and then use a cofactor from, say, the second row. Okay, so 2J of A. So to do that, this is equal to, well, A11 is 1. And then the cofactor here, now I need to remember my -1, so this is -1 to the 2 plus 1, because I'm doing a cofactor of 2J. And then I need the 2 and the 5, that multiplication, so 2 times 5 minus 3 times 1. Okay, so I have that one. Then plus 2 times -1 to the 2 plus 2, and times 1 times 5 minus 0 times 4. And then plus 3 times negative 1 to the 2 plus 3. And again, that one I get 1 times 1 minus 0 times 2. And so we get a negative 1 here. So we get minus, and I have 10 minus 3 is 7. So I get minus 7 for that first part, plus 2 times negative 1 to the 4th. So that's just a 2. So I've got 2 times. Here I have 5. So 2 times 5. And then plus, I'll get a negative 3 from those 2 parts, and then times 1. And so indeed I get negative 7 plus 10 minus 3 is 0. So we see that we do get 0 from doing that. That is a very nifty theorem there, is that if I expand by any given row or column here, I picked that one, but I could expand by that one, that one. I could do it this way, this way, this way. It doesn't matter that if I expand by a given row or column, but then I use a cofactor from a different row or column, I will always get 0 for that calculation. So that's interesting, okay? So you will always get 0 from that.